So I'm going to get started here. We're looking at exponential functions. And what we're going to look at are any power function. So f of x is some base to a power, and the related inverse function. Where we have a log of the same base to x. And we're going to look at the relationships and the models that get used for these. And we kind of want to think of some of the rules that are going to come into play for us here. So the rules I want to put up, and that way I can flip back to them periodically. Putting these up here. Let me just show you what I'm doing while I do this. So I'm listing all the rules of exponents and their related exponent rules, because we're going to come back to these rules over and over again. These are our power rules of exponents. And they have similar log rules. Log 1, 0. Came near the microphone there, sorry. Let me just get my log rules here. And then, let's see, I want this side of it, so B and then there's the inverse rules. Let's see if this is still, yeah, this is still showing on the screen. Log of some base of base to a power gives you x, and some base of log base x gives you x. And you'll find that these are the magic sauce that we're going to refer back to. So I'm going to keep those up here so I can get back to them easily, since Blackboard's going to be off to the side, different from the electronic Blackboard. But what I do want to point out is we've had these exponent rules, started very early on with the exponent rules and how exponents work. And because the log is the inverse of an exponent, there's a similar form to these rules. And so as I add these new rules in, I think of them in their exponential form, in their log form. And so if we have an addition of powers, that came from a multiplication of the same base with powers. And here I have logs adding turn into a multiplication. So because a log is an inverse of the exponential, we want to be able to see these go through. Kind of neat, disembodied hand. Guess I have to, yeah, there we go. But I have these up here. I'll come back to them periodically, because these are the rules that we base everything off of when doing logs and exponents. But for right now, I want to look at this relationship between these two things and look at some particular models. we have seen the doubling time and half-life time. And so we're going to start with half-life. Let's see here. Log. Yeah, I'm gonna look at some particular models and move into how these rules go together. But the first thing I think I want to do is I'm going to take these rules and show the usefulness for them for logarithms in general, and how this magic sauce here and this particular function where n times log base b of m is equal to log base b of m to the n can help us, and it can help us do something that we've had a problem with. And so I'm going to talk about your logarithm being the inverse. So we have the log base b of some function is the inverse. Now your calculator only has two keys for these. You have an ln key. I'll keep it going left to right. So if I have e to the power, its inverse logarithm is ln. Its inverse function is ln of x. And this is saying underneath the hood that this is log base e. And this is called the natural logarithm. And then 10 to the x is log with no base written. And underneath the hood, that's log base 10 of x. And that's called the common logarithm. If you watched lately, there's been some things that have been using a log scale, which means each line on the graph is a power of 10. So if you're having a graph like this is 10, this is 10 to the first, this is 10 squared, this is 10 cubed, and so on. And that's called a log scale because each jump between here gets 10 times further, 10 times further, and it's actually a log base 10 scale. And they're actually quite common scales when dealing with exponential things because if you look, I posted a video for a question on one of the homeworks which asks to find the intersection of the function 1/2 to the t divided by 5,700 when that intersects with the line is 0.16. And it asks you to do it graphically. And the problem is this function 1/2 t to the divided by the 5,700 is hugely sloped. It looks like a straight line near zero. In fact, they intersect somewhere in the 15,000s. And so when you're looking at it, this is so steep, this rise is so fast that when you're close to any part of it, it looks like a straight line. And log scales were invented to kind of straighten these curves so that you didn't have that problem. But you have to realize everything goes by base 10. And that's from the common logarithm. It's commonly used log. But your calculator only has two keys for them. And the nature of that is, I have b to a base and log b, the base. I can have an infinite number of bases. And before calculators were invented, when people had to do these things initially, they needed to do them through printed tables. And having a resource that had the answers already printed, they would make these by hand because getting the inverse function to a level of precision took you doing the calculation in one direction and then in swapping your range and domain. Because of that, we can't print infinite books yet. The internet's getting us there, but we can't. And so there were common numbers used, and the natural logarithm e you'll find I use a lot because E as a function has some very unique calculus principles that make it very, very useful in many different fields, and especially differential equations. So a lot of answers to differential equations, we use the function. We'll have some functional form of e to the x in it, whatever is around it. And because of that, the natural logarithm is very, very, extremely useful. It's actually a large reason this is taught at this point in time in a functions/algebra class. Is if you take no other mathematics, you're going to be dealing with exponentials and logarithms from a functional use. That the answer is supplied somewhere, and you're going to have functions that use these things. So it's good to have an understanding of them themselves. If you're progressing further in mathematics, the exponential and the natural exponential with base e is probably one of the most useful things you can exploit. There we go. So we only have 2 keys on the calculator. So there comes a problem of what happens when you want log 2 of 58. You have no way of getting the answer with the calculator. Now, some of the more expensive models and some of the computer software, you're able to specify the base, but even most computer software will use the natural log exclusively, and you might have to do some different keystrokes to get the common log. So how do we trick the calculator? And we're going to go back to these rules. Here, we're going to use these rules of logarithms. I'm actually going to put a dotted line between the exponential rules and the logarithm rules, and then these are our special ones. Special ones are going to help us get through, but we're going to use these rules in tandem with these to let us solve. And it's going to show us what's going to be known as our algebra with logarithms. So I'm going to make this in a very generic form. I'm going to say that I am going to have some answer is equal to the log of a base that I do not have a key for on my calculator. And I'm going to put into that my functional value of x. Now I want to do a trick here. That is the trick in algebra, and you hear me, I say it as nauseum a lot. Whatever I do to one side, I do to the other. There's a neat thing we can do. I think I'm going to particularly go for the natural log first, and then I'll show you this with the common log. But if I have x is equal to 5, it's fair to say that e to the x is equal to e to the 5. Look at that for a second. X equals 5 is a statement. I'm making that. If that is true, if I take e to the power of whatever this is, that would be the same as e to the 5th. Substitution tells me wherever I see x, I can put in 5. It also tells me wherever I see 5, I can put in x. And so this equality holds true. So we can look as the function e, the base of the natural base, as being an operator. I can do the operation of taking this side as a power to e. Could also do something similar. If x equals 5, I could say the natural log of x is equal to the natural log of 5. Because whatever I have for x, I could replace with 5. My equality would stand through. And so these functions can work as operations. If functions hold true, whatever I spill into them gives me one answer, which is what we made our functions do, right? For each x value, we get only one y value. Then whatever I put in here has to equal if this was true. So I'm going to use that to my advantage. I'm going to say, you know what? I would prefer to see this. In fact, I'm actually going to be a little more trickier. I think I want to take it to base b. B to the y equals b to the log b of x. I like that better because that's going to let me do the trick here. Let me get to my switchy. All right. If I have b to the log base of b of x, they'll cancel back out. I'm using the inverse property to be able to cancel and move things forward or backwards. So, what I'm able to do by forcing this, and I can use that inverse property, I've changed my left-hand side to an exponential. And this bit here, because it's an inverse, leaves me with x. I've really written my logarithm in what we're going to say is exponential form for the logarithm. Yeah. So I'm going back to the rules that we have for logarithms. The rules, they actually give you your textbook page where these rules are screened at us. They're on page 458 for the logarithm, the rules that we're using. All right, well, if I'm free to take something to any base, I'm also free to take any logarithm. My calculator only had two log keys, natural log and common log. So I want to take the natural log of the left-hand side. Notice my wording there. I'm taking the natural log of this number. But whatever I do to one side, I do to the other. So I'm now using my logarithm as a function, a functional operator, and I'm exploiting its properties. Whoops. The next property I want to explore is this power here. I have now made it so that I have a logarithm to a power, and that power was my variable y. Well, the other side of this equation says that that y can come out in front of my logarithm. And so here, I'm going to use that power rule. I'm going to put y ln b equals ln x. Notice what I've done. I've done this odd trickery where I no longer have the log of the base that my calculator doesn't have a key for, right? All my logs now are in terms of what my calculator has a key for. And here I was stuck with my variable in the exponent. By taking the natural log, this multiplication rule lets me pull this down. And we're going to find we exploit this a lot when we need to pull powers down. We'll take the natural log or the common log or a log of some base of what has our variable in the power, and that multiplication rule will let us pull it down. Well, now I'll divide both sides by the natural log of b. And we get what's called the change of base formula. This y is still equal to that y. I initially started with a logarithm in a base that my calculator didn't have the key for, and I have an answer in terms of a base that my calculator does have a key for. Notice my original base becomes in the basement of the fraction, and the original term is up here. Well, what if you can't find the natural log key? So I'm going to take all my steps down to here, and I'm going to change over to a pinky color. And I'm going to come back with the b to the y equals x, and instead of taking the common, or the natural log, I'm going to take the common log. I'm just going to say, hey, I'm going to take log base 10 of b to the y to this side, and whatever I do to one side, I do to the other. So I take log base 10 of x. My property of logarithms doesn't matter what the base is, so this y still multiplies back out front here. And I'll divide both sides by log of b. And I have my change of base with log base 10. In fact, the general change of base formula, bright red here, is, no, bright red ain't working for me, green, not sky blue. My y value is equal to the log of some base I have on my calculator. Let me just, I'll say, I'll get the log in some base I don't have to some value x. That is equal to what I have on my calculator, x, over what I have on my calculator, what the original base was. Now I know the calculators have these two keys, ln and log. So I use them specifically. Well, let's look how this works. I want a very common logarithm that comes up. Let's just do, log base 2s happen a lot. So if I want log base 2 of, well, we're counting by 2s, let's go with 15. And I go over to my calculator. You'll notice here, right, on the calculator, let's see if I can get this. Let's see if we can get the keys in. There's the keys. I've got two log keys, log and ln, right? But I don't have a log base 2. No log base 2. So, sorry about this. There we go, sorry. And no log base 2. So, if I want to do a log base 2, I've got to change into one of the two keys I have. So I use this formula I figured out, because we're clever eagles and we used our change of base rule. So log base 2 of 15 is the same as the natural log of 15 divided by the natural log of 2. Well, let me do that on my calculator. So ln 15 divided by ln 2 is 3.906.891, and so on. Make that an approximate. I'll just leave it there. But Jeff, you said it was the same as log base 10. Well, let's do that. Let's enter that on our calculator. Let's enter log 10, 15 divided by log 2. So I hit the log key instead of the ln key of 15, and I divide it by the log of 2, and lo and behold, I get 3.906891. So our change of base formula works for us, and it works no matter what base we choose. You will find I run to ln. When in doubt, I run to ln. All right, so what we want to do here is we want to develop our function algebra and use it to build some models using these things. So we kind of want to use these properties to help us out and develop the different mathematics we can do using these function rules. And so a lot of the times we find ways of expanding expressions or taking a logarithm and breaking it apart into pieces. And I'll kind of give you a why. I'll show you some examples and we'll go why. So again, the rules that we're going to keep coming to are these over here. When I have log of 1, it's 0. When I have log base b of b, it's 1. Log base b of some number plus log base b of another number is the same as the log of the two numbers multiplied. And any rule that we have is reversible. So we're able to move these rules backwards and forwards. So let's show you what I mean. So I can be given some log of x times y. Well, my rule of multiplication, log m times n, says it's the same as log m plus log n. So that's the same as log x plus log y. And you're like, well, why? Why would people do that? Well, this is log base 10, right? So if I had log of 150, right, I would have to go and calculate on a table what log 150 was. But I can notice that 150 is the same as 15 times 10, which means log 15 plus log 10. But this is base 10. So this is the same as log of 15 plus 1. And what this allowed people to do was figure out patterns. As your multiples of 10 kept going up, you kept adding ones onto it. And so you wouldn't have to make a table or a value for each number. And this leads to some quick calculations you can do, especially when you're using log-based things like pH values. And you're learning to count the number of whatever your base is coming across here. And so this is how this rule tends to get exploited. But sometimes some of our algebra comes through very oddly. So some of our algebra might create an expression that we need to simplify like this. Let's go here. So I'm going to have log of the cube root of x divided by the square root of k. And this comes back to my pet peeve. I do not like this notation for writing roots. We're stuck with it. Hundreds of years of it. We can be the generations that change this, but it's the same as saying x to the 1/3. And I like the 1/3 because I get all my exponent rules with it. And log of k to the 1/2. Fractional exponents are so much better than radicals. That said, I'm going to use the division that's happening here to write this as log of x to the 1/3 minus log of k to the 1/2. Then I'm going to use my power rule, and I get 1/3 log of x minus 1/2 log of k. And people, when they were doing their mathematics, did these to get rid of having to take square roots. Right? They could turn them into a multiplication by a half. The whole purpose of logs and log calculations were set up so that mathematics could get easier for people for certain higher level things, powers, square roots. But you had to have a table of what your log values were. So you pushed all your problem into having the table here instead of having to do cube roots. You know, well, if I know what the log of the number is, I just take a third of that. And that's the utility of this type of expansion is our algebra might give us something like this. Now, calculators have made it slightly easier for us to do some of these because the calculators take the formulae for us and answer them out. But one of the things about expanding and collapsing logarithms that will be very, very helpful is that it saves how much you have to type on a calculator. So this one here, log, and then you have to hit this key, put the 3 in x. Make sure you get your parenthesis, exit out of here, and exit back to here. But before you exit that parenthesis, you have to hit your division key, then your square root key, then your x, make sure your right arrow, and then input in there, right? And so one of the things is as your function becomes a little more complex to type in, you have to watch your grouping symbols on your calculator. And simplifying, expanding these expressions can avoid error, and they can help put it into chunks. Also, if your logarithm's coming out of a physical system or is going to go back into an exponential system, there are chunks of this that will fall through. So the skill of using these rules is much more useful than it appears. But I think any new mathematical operation, the utility comes the more you do it. All right. So that's called expanding. When I take one logarithm and I take its parts and crunch it out. Well, the opposite can happen. We can express a logarithm in terms of one function. And here's a good example of that. I have the natural log of 2e plus the natural log of 1 over e. So I have something that's somewhat expanded out, and I want to condense it down. I want to make it smaller. Well, addition tells me that I have multiplication going on. So I have ln 2e times 1 over e, or the ln, and I'll put these in parentheses to realize it's the natural log of these two things multiplied. The e's cancel, and I get ln of 2, which is about 0.69-ish, I think. 0.68-ish. It's halfway up a curve. 0.693, yeah, 0.693. Sorry, knowing kind of where about these things are can be helpful. All right, let's look at a couple more compressional forms of algebra. So log base 10 of 5 plus log base 10 of 15 minus log 3. Well, we can do this a couple ways. I'm going to take the additions as multiplication. So I'm going to get the log of 5 times 15 minus the log of 3. But the subtraction And again, I'll go back to this here. Subtraction, log base m minus log base, or I'm sorry, log base b of m minus log base b of n is the same as dividing m and n in the same base. And that is parallel to this exponential rule that we have. So I can take the subtraction and turn it to a division. So log of 5 times 15 divided by 3. And now this is all trapped in my log function. The 3 and the 15 cancel, giving me log of 5 times 5, or a log of 25. I think technically, right, that's 5 squared. I think people would see it as this, because this would be easier to look up in a table and multiply by 2. But when you want to collapse it down to one term, that's probably the better answer. And so there is an algebra we do with these things. There are properties of logarithms that let us do algebra with them. And they actually help us when we work with our particular models that we're going to get out of these. But let's look at the algebra that comes about from these. So we've been doing them with certain numbers. We're going to pull all of these into particular models, but let's first work on the algebra of this. And I actually think I'll use a model for it, because I use this a lot. So one of the things that I said when we were looking at a doubling model, and I'll actually do radiation, I'll actually do 2 exponential models. I'll compare 2 exponential models that are similar, and we can see the utility of this thought process. And so 2 exponential models. Growth and decay. So for the growth model, I'll think of having one cell that splits into 2, or some population bit that splits into 2. And the length of time for that is the doubling time. So for right now, just call it T double. It's a doubling time. Now the other thing that can happen is I could have a radioactive substance or something that is decaying. And so these will break down into lesser components, so they'll leave the group. And so we'll say when they break down, I'll just put X's on them, and that'll leave me with 3 things. And so there's some time where I get half, and we call that the half-life. And these models are very similar. Now, when we first modeled them, I could say, hey, this can be some function of my initial amount times 2 to however much time passes divided by the half-life. And that's a good model. To take everything to the power like that is a good model. Problem is, base 2 can be hard to work with. This model over here, when we first look at it, and actually I'll put, you know what, I will change, since this is growth, I will make this G, function G for growth, right? We'll name our function to help us here. So this will be function G for growth, and this will be function D for decay. And I have some original amount of substance that gets multiplied by 1/2 to the power of how much time has passed divided by the half-life. And that's a good functional model for it. But 1/2 as a base, we don't have as much tables for. Well, there's a couple things I can notice here that might help me here. Both of these start with an original amount. And I'll put 2 to the t to the... So growth, and nothing I'm going to change here for growth. If I want to make decay look like growth, wouldn't it be nice if I could turn this into a power of 2? Wouldn't it be nice if I could turn that into a power of 2? Well, what is 1/2? 1/2 is 2 to the negative 1. So I could say this is a to the 2 to the negative t divided by half-life. Well, this is nice now. Nicer, right? Let's notice these things are kind of sort of the same now. Kind of sort of the same. They've got the same base, and the only difference between t divided by the doubling time and t divided by the halving time is the sign. So models of growth have positive exponents. And models of decay have negative exponents. Well, that's good to know. I'm definitely having less things to memorize as I go through here, right? Remember me, I don't like memorizing things. And so if I can use the same form of something, and the only thing that changes is a sign, that makes me happy. That means when I have a word problem, and I'm looking at it, and my money is growing, I don't go, well, what was the equation for interest compounded continuously? I go, that's exponential growth, so I'm going to have a base to a positive exponent. When I'm looking at a bacteria growth rate, I'm going, that's a bacteria.